Now I have my dear colleague and good friend, Deyan Draganov here, to also further get to the depth of this subject with us. Deyan is Associate Professor in the section of Applied Geophysics in the Department of Geoscience Engineering that I also work in the same department. He's currently co-supervising many PhD students and postdocs. Since 2004, Deyan's research has resulted in 70 published papers, 1 book publication, and 5 book chapters. In 2010, he received the J. Clarence Carter Award from the Society of Exploration Physics, SEG. In 2021, Deyan received Outstanding Educator Award of SEG as well. He was awarded VENI and VD as well. These are prestigious individual grants in the Netherlands. Personal grants by the Dutch Research Council, NVO. From 2006 to 17, he has served as associate editor for the Journal of Geophysics, and from 2017 to 19 as assistant editor for the same journal. Currently, he serves as associate editor for the Journal of Geophysics and Engineering. He's member of SEG and European Association for Geoscientists and Engineers, and is a founding member of ModNet Group. So thank you very much, Deyan, for accepting our invitation, and we are looking forward to hearing your lecture. Thank you.
Yeah, thank you for inviting me to give this lecture. I'm really happy that I can. It's also just like Eric first here, it's a different audience, and it's a good possibility to meet each other, also with some of you also in person. Before that, we have met only through screens, through different meetings. And now we have the possibility also to start discussing what we know about hydrogen, what we do not know, or do we know already everything, and we can directly start with injection and cyclic injection, and just there are no surprises that we can expect. Everything is clear. Well, Eric already yesterday started with introduction of geophysical monitoring, and he showed really state-of-the-art methods that can be used, and what he said, yeah, you cannot beat the active source seismic method. It's true. I also agree with that. But sometimes we need also some alternative to have, also triggered by one of the questions, well, how often we have to monitor? Do we monitor once a year, once in 5 years, every week? Well, this is something that maybe we don't know. Afterwards, during the discussion that we'll have after this presentation, then we can start talking about this. So here I am going to present alternative monitoring techniques using seismic interferometry. And as I said, if we have active sources, that's the best. But sometimes we might not have them, so then possibly with passive sources. There was also such a question yesterday. First, I'm going to tell you quickly what is seismic interferometry with a few cartoons to introduce you to the idea, and then I'm going to show 2 examples, only 2 because yeah, we are limited in time. Eric was too generous yesterday to say that I'm going to show a lot of things, but I had to limit myself, so only 2 examples, one with active sources. If we have them, that's really good, and then we can use them in a different way to really come close to our reservoir and take a close look at it, what happens in it. Which means that then we might be able to say more about the reservoir, not to look at it from the surface, but close to it. And the other example is when we don't have active sources. Then what do we do? How do we monitor? Well, then we can use what we have, and what we have is seismic noise. And that is something that could be very useful if we know how to use it in the right way. And then we are going to draw conclusions. But what is seismic interferometry? One of the most general definitions, and the one that is mostly used, because then it's easy to apply it, is that it is a method that retrieves new seismic responses at receivers from the cross-correlation of existing responses, recordings at those receivers from surrounding sources. Let us, for example, have here sources at XA and XB, put somewhere in a complete medium D, and then these 2 receivers are surrounded by a sphere of sources. And so we have on this sphere distributed sources in a good way everywhere, the same source, so they illuminate the receivers in the same way. Then we can, for example, take the recording from these receivers at the from these sources at the receiver at XA and correlate it with the recordings from these sources at the receiver at B. And then the result will be, after a few mathematical processing steps, that we will obtain actually a virtual source at the position of the first receiver at XA. So we'll turn the receiver into a virtual source. And then from this virtual source, we'll obtain recordings at the other receiver. So this, you can already start seeing that it might be advantageous when we want to have more sources somewhere where we could not put them at the beginning. When we have our Earth, of course, normally we record from the surface of the Earth. Yeah, then we can have our receivers at or close to the surface. In this case, it can be shown that we don't need to have our receivers completely surrounded by sources, for example, to have also sources in the air, but we need only sources in the subsurface. That can intuitively be seen and understood by thinking that our Earth's surface for seismic waves appears to be like a mirror. So when a seismic wave comes to the surface, so the energy is completely reflected back for our practical purposes. So in this way, if there are sources below this reflecting mirror, then also we know when we look at the mirror, if we have something behind us, it appears also that it is also in front of us, the same thing. So in this way, the Earth's surface plus the sources in the subsurface make a closed surface of sources, so our receivers still stay enclosed effectively by the sources. And then we can turn one of them into a virtual source and then retrieve at the other receiver the seismic response that we want. And this is geometry that we'll see in the second example when we want to use, or I'm going to show how we can use passive sources. In this case, possibly micro-earthquakes, for obtaining an image of the subsurface. Another possibility is that we have our sources at the surface, but we have our receivers in the subsurface place, for example, along a well. And then it can be shown that the main contribution to reflection arrivals, like this one that I'm showing here, if we want to have reflection arrivals from our reservoir, then the main contribution comes from these sources at the surface. And that is something that we are going to see now in the first example, how we can use this situation for taking a close look at a reservoir so that we can see what happens with it in the course of time, in this reservoir in the course of time when we do something to that reservoir. And this is an experiment actually that was done in 2002 in Canada in the Peace River field. It is oil sands field where they have at a certain depth sands with bitumen, and then to produce the petroleum from that reservoir, they have to stimulate it, and they do it with steam. So in a layer under the reservoir, they inject steam that heats up a bit the layer above it where the bitumen is. Then the bitumen becomes less viscous, and then it can be produced. But that, you can imagine, already creates something in the reservoir, something changes in the reservoir. And they went and made a recording. This was done by Shell, actually, in 2002, in September, before the steam cycle. And then a second survey in December, so 3 months after the steam cycle, so after the first survey, after the steam cycle finished in December, a second survey, what we call a monitor survey. And the idea is to see what happened to the reservoir. Was there any change at all due to this stimulation? Yes, no, let's see what happens. They used sources at the surface, 100 sources really along a line at the surface, and main target was to actually place here receivers in a slanted well. And as Eric explained yesterday, how we do these surveys in wells, we put geophones, we record at certain level, then we move them to another level, we record there. So it is quite tedious operation. Here, also, as Eric said, if we have an optical fiber cable, that can help a lot, because then we instrument the complete well, and then we record wherever and whenever we want. So here they had 53 component geophones, what we call, so seismic receivers, which are sensitive to vibrations in the vertical and the two horizontal directions. And these receivers were 9 meters apart from each other along the well, while the sources were 12 meters apart along the surface. And the sources, Shell really took a big pain there to make them repeatable, which means that they drilled holes, and inside these shallow holes they placed the sources, and they set them there to stay all the time during the monitoring campaign, the base survey monitoring, so that they eliminate this non-repeatability, what we call, of the sources. So if I talk now to you, and you record this, and if I say the same thing from the same place in 1 month, you will hear exactly the same thing. But if I move to the side, maybe Hadi there is not going to hear the same thing, because I am directing my waves in this way, so he will notice a change possibly, but then the change is not really there, not because I changed my mouth, but just because I stepped a bit to the side. This is what they were actually experiencing there as well. Despite cementing the sources, there were still changes in the source function, so what we call, so how the function of the energy that we send from the source in time looks like. It was changing just because things were changing around that hole. And actually what was changing a lot was the complete, what is labeled here, complex near surface. What you see here, this is the one-dimensional model of the subsurface, which was built using the active seismic data, geological data. And actually the near surface, which is not interesting at all for the reservoir, brings a lot of changes, especially between summer and winter. They have those glacial deposits there, and that makes a big trouble. So it actually obscures the image of the reservoir. It makes differences between one survey to another survey, really big differences. So the idea was to actually redate them with seismic interferometry, the surface data, to virtual source data along the well, and then also to have the recordings from those virtual sources in the well along the other receivers in the well, to see if that can give a better image of the reservoirs, of the reservoir. Here you see just quickly what the authors have done as processing steps only to obtain the virtual sources in along the well, close to the reservoir. And you see it appears quite easy. First, we select a place, so an XA, where we want to have our virtual source, what we call a master recording, because that receiver, we take that recording, and from that recording, actually, we choose only the direct wave coming. So from the sources at the surface to that slanted stack, this direct wave that comes, we only extract that arrival from that recording. And using that recording, we correlate it with, so this master recording, we correlate it with the rest of the recordings along the 49 other receivers along the well. And then we repeat this for each of the sources at the surface. And at the end, we sum the separated correlated results, and then we obtain one virtual source and recordings along the other receivers in the well. And of course, we then change the virtual source position to another receiver position along the well. And here, in the top, you see the seismic interferometry result, which shows here in the ellipse the reflections of interest from the reservoir. So now you can see this is time. So actually this is 0.1 seconds and 0.2 seconds here. The reflections that we expect are now very close to the source. Why? Because we moved from the surface to the well, which was much closer to the reservoir. This is the seismic interferometry result. This is a result which is numerical modeling. So the authors decided to compare this, which they were quite happy with it actually, or very happy. They want to compare it just to be sure to know what they're seeing with numerical modeling results. So they used this the velocity model that I showed before. They put a source along the well at the receiver of this virtual, at the receiver position of this virtual source, and exploded the source, modeled how the wave fields propagated in the subsurface, and this is what they got. And they also saw here, but for the base survey and monitor survey, that they expect really changes, visible changes. And here one can see them as well, that these reflections are different from these. Another difference, what you see here, is that actually in the modeling we have this, like this is a direct wave. So along the well, this is the virtual source. We have a wave going up along the well, a wave going down along the well. These are these two legs that we see here. The downgoing leg we do see also in the retrieved results. The upgoing leg we don't see. How is that possible? Well, this is only possible because we chose to have sources only at the surface, not, as we said, actually, according to the theory, we want to have them everywhere, surrounding our receivers, and now we have them only on top. As I said, yeah, that's what we want for reflections. Yeah, we miss half of a direct wave. We are not even interested in a direct wave, so why should we have it? An extra added value. I do not show here comparison with, direct comparison with the surface data. Actually, I didn't say that when they were recording that data, they also had simultaneous recording with receivers at the surface, not only in the well, but also at the surface, to try to image and see, compare how the two things can image the reservoir. I'm not showing it here, the comparison, because the authors themselves did not show it, because it was not that great. Here, there is a comparison. So after having this retrieved results, so this is what we call a common source gather. So we have a source at one position, and all the other positions we have receivers, and we see how we what arrivals we have at different times away from the source. When we have this at all virtual source positions, then we can apply some imaging algorithm, like yesterday what Eric Verschuur was showing, like joint migration inversion or full wave field migration. Well, at that time, the authors did not have those advanced methods. They did a more standard one, actually very good one. Standard processing, what we call pre-stack depth migration, again, state of the art. And this is what they obtained. And you see here the top of the reservoir, the bottom of the reservoir. This here to the right, so this is the base survey, this is the monitor survey. And we already start seeing that this reflector, the top of the reservoir, is not the same as here. So we can see changes, which is possibly a good thing if these changes can be attributed indeed to the reservoir. This is the data that was obtained using the sources at the surface and the receivers in the well, but without applying seismic interferometry, directly applying pre-stack depth migration. And, well, because the changes in the reservoir due to the stimulation were really big, something that we don't have that often, and that's what Eric Verschuur was mentioning yesterday. We need to have a few percentages of change to see something. Here it was quite a lot of percentages of change, so it is also easy to see it with naked eye in the normal active data. And we see here the top of the reservoir, the bottom of the reservoir. We see that these amplitudes here are weaker compared to this one. And that happens because due to the stimulation, the parameters inside the reservoir changed, and actually more energy is being reflected back. So we see it as stronger amplitudes, brighter amplitudes. What we do see here is, yeah, the top of the reservoir, bottom of the reservoir, and that's it, nothing more. Well, we still again see that this bottom of the reservoir appears here to be coming earlier compared to the monitor survey after the stimulation, which is again good. So something happened also in the reservoir, but we cannot say what happened because we don't see what happened in the reservoir. While here, the extracted value of interferometry, so redatuming everything to the well, so pushing our sources from the surface to the well, we eliminate the propagation times of the wells when they pass through this complex near surface, which can also make our image much less clear. It can be compared to, for example, looking at a painting in a museum, and if we can come closer, we go to the painting to see the different strokes that the painter did, to see how it is, the details, and compare this to, instead of going close to a painting, going further away, and on top of this, putting between you and the painting several dirty windows. What are you going to see? Well, that's what we see here. We have the near surface, the dirty window, which makes it difficult for us to understand what is in the painting. We do see the big picture. Yeah, it's a house. But what house? Well, actually, the seismic interferometry result here shows us that it's a house with several rooms, we see intra-reservoir reflections here, which here, of course, are invisible because they are not there. Still, is this a real thing? Or is just a wishful thinking, still some artifact due to the near surface, but we think it's the reservoir? Well, to check that, the authors looked again at the seismic interferometry result, but retrieved reflections and imaged structures above the reservoir. And they see that for the basin monitor survey, just above the reservoir, or between the well and the reservoir, there are other structures, and there, nothing changed. You can see that the two pictures are nearly exactly the same. Even different aberrations are quite comparable, which shows that if we see deeper, so where the reservoir is something as a change, then it must be attributed due to change in the reservoir. And that's what the authors did. So they went and zoomed in at the reservoir base survey, monitor survey. So these are the seismic interferometry results after redatuming the source at the surface to the well. And what we can see is actually now a well inside, fault inside the reservoir. And it really shows good compartments to the left and to the right. We see actually that due to the stimulation, the changes happened in the parts of the reservoir 1A and 2B. And actually this data, by seeing that changes happened between base and monitor survey on two sides of something, confirms independently that there is a fault, which does not allow or allow only specific movements inside the flows inside the reservoir, but not everywhere. So this is really showing good added value, or very good added value, or great, depending on the person. If you ask me, great, but it's up to you to decide. This added value of this method. So you have your active source data, you can redatum it close to your reservoir and then look close at your reservoir. And you can use not only pre-stack depth migration, you can actually go further and use what Eric was proposing, joint migration inversion, and then you can possibly get even better images. So, as we all both said, yeah, having active sources is great. We want to have active sources. But what if we cannot have them, or we can have them, but only on yearly basis, and we still want to monitor underground hydrogen storage every week? Yeah, well, we cannot have the active sources. It's way too expensive. What can we do? Well, then we try to do it without the active sources. So we go back to the situation where we have receivers at the surface, we place them, and just let them record. What we will record, of course, is the background seismic noise. If I walk, that's background seismic noise. The receivers will hear it. The wind, there is background seismic noise. But there are other things as well. There are traffic noise, which can be useful or not, depending for what we wanted. There can be local seismicity, that can be very useful for our purposes. There can be induced seismicity, also very useful, and other sources of noise. For example, fighter jets flying over. We have seen that, and then also that you can use. Actually, it can be shown with seismic interferometry that if we have sources in the subsurface, as we said in the theory, we want to have sources here, everywhere in the subsurface along a hemisphere, and then we can retrieve nice reflection response, turning one of the receivers at the surface into a virtual source where we didn't have at all a source. It can be further shown that if we have sources nearly vertically below our receivers, then we can mainly retrieve reflections. And if we go a step further and use not cross-correlation but auto-correlation, which means we take a recording in one receiver and correlate it with itself, then we can retrieve actually post-echo measurements, virtual post-echo measurements, turning a source, receiver into a virtual source, and at the same time we record at the same receiver its response. Examples of such post-echo measurements are echo soundings in the sea, to see really the bottom, how it looks like, or even in medical imaging, echo sounding for pregnant women to see the baby along a line, and then you see it. Here we can obtain directly from the noise post-echo measurements at the receivers. What is the advantage of having what we call zero offset measurements? The advantage is that we directly get an image of the subsurface. It will be in travel time, not in depth, but okay, then the conversion to depth comes when we have a velocity model, and that could be there from geology or other, from the active seismic measurements, for example. And I'm going to show here an example from data that we recorded in 2001 in July in Iceland, actually in Reykjavik, close to Reykjavik, in Iceland, in the Hellisheidi geothermal project. You can see it in this picture where it is, and there we placed receivers every 25 meters along two lines. You see here the blue and the red dots, these are the two lines here. And then we recorded noise for 120 hours, so 5 days. The idea was to, this is actually part of the Succeed project where the main goal was to use active sources and then to monitor changes in the subsurface when we, or when the geothermal company there injects CO2 in the basalts for permanent capture. They become part of the basalts, I saw minerals there, and they're permanently captured. And what happens then? The CO2 is captured from the geothermal operation itself. And we recorded also passively to see if we can see something from the subsurface. How is the processing to turn our receivers into virtual sources? Well, actually, it's quite easy. We evaluate whether a specific noise panel, what we call a noise panel, we have the 120 hours of noise recording, and we extract a short window of it, 10 seconds, for example. And then we check if in this 10 seconds window, if we have a specific arrivals, which are, as I said, vertically below, so coming nearly as a vertical incidence at the receivers. And we do this simultaneously along both lines. And then we can really be sure that this is something that comes from below vertical. And that's what we want. Then, if we have this panel with these arrivals, then we autocorrelate that panel, and we keep it. And we do this for all these 10 seconds noise panels. And then, at the end, those autocorrelated noise panels that we kept, we sum them together. And then we retrieve virtual zero offset measurements or pulse echo measurements. And you see here, directly, they give us an image of the subsurface. It doesn't look as spectacular as Eric was showing yesterday, but we'll see that actually it's quite good. This is the image that we obtain below this line. And we can see already some horizontal arrivals here, which is something that we expect. And how do we know it? Well, this is the geological 2D section. We can compare it with this geological 2D section, which is extracted from the volume that they have built here along different lines, and this is done using extensive boreholes that they have there. And along this 2D section, actually the extent of our seismic line is this yellow rectangle. And you can see here that we expect to have subhorizontal reflectors. And that's what we see also in our image. I'm showing here examples of just two, so if you follow with your eyes in these two transparent rectangles, violet rectangles, you will see that there are things, so such aberrations, black amplitudes that make a nice line, for example, here. But there are also earlier and later arrivals, like here and here, for example. So this shows that actually we were able to image the subsurface with passive measurements, just 5 days of noise recorded. And this is along the cross line, the other image, so along this line here that you see. Again, we see clearly some horizontal arrivals, and again here you can see that in this part of the 2D section, which is now extracted from here, we again expect to have subhorizontal arrivals, and that's what we have here as well. Clearly visible, and also deeper, but shorter structures, possibly something like this. And again, this is built using borehole information, but then interpolation between the boreholes by geologists. And that brings me to the conclusions, which afterwards maybe we can use even to start our discussion. So seismic interferometry provides advantageous alternatives for monitoring subsurface changes close to reservoirs, for example. Seismic interferometry can be used with active sources at the surface to retrieve virtual sources along a well, for example. And that will allow us, as we saw, to see a better high-quality image of our reservoir and possible changes in it, or not. We can detect that as well. We can also use seismic interferometry with passive sources, for example, microseismicity, be it local, natural, or induced. And then we can obtain directly pulse-echo, virtual pulse-echo measurements of the subsurface, and then directly get an image of what is below. And if we have, I showed here one image from 1 year, but if we have several images, if we record not only 5 days, but 500 days, and we can see the 100 images and see what happens. And that can give us possibility for cheaper and more frequent monitoring of the subsurface. Oh, thank you.
Thank you very much
for your attention.
Yeah. Thank you. The images you showed, and then you said, clearly we see that reservoir. It reminded me that
these are
we expected a baby, and they were doing ultrasound on my wife, and then said, yeah, clearly the baby is here. I said, if you say so. I mean, I don't see it. Clearly there was a reservoir. Questions? Here we have Chris.
Much of our new energy infrastructure is co-located, so we'll be storing in the same places that will have, other things to help the energy transition. Could we use wind turbines as a continuous passive source?
Yes, that is what Eric actually hinted about, that I'm going to show today, using surface waves. So the wind turbines are at the surface. When a source of noise is at the surface, the main energy that we can retrieve using seismic interferometry are surface waves, so waves that propagate along the surface. And they are called surface waves because they propagate along the surface, but they still have a wavelength, so they see in the subsurface as well what happens. They can be very advantageous for monitoring really tiny changes in the subsurface, but we have to know where those changes have happened. There are ways to do that as well. The limitation there, though, is that we are limited by this wavelength of the surface waves. So we can use surface waves to say what happens to the subsurface parameters, the wave velocity, what we can obtain. Let's say between half a wavelength and 1/3 of the wavelength. So that's our depth target where we can see something. If we use wind turbines, then let's say that we have possibly frequencies down to 1 Hertz. Let's be very optimistic. Depending how far we are, actually we see frequencies higher than that. But if it is 1 Hertz, because it's easy for calculation as well, then our wavelength for depends on the propagation speed or propagation velocity of the surface waves. If we say that it is 1,000 meters, very optimistically, so this is possible if we are, for example, in Iceland, really hard rocks, then even there, actually, it's a bit lower, but let's say 1,000, then our wavelength is 1,000 meters, so we can see things between, so down to really optimistically down to 500 meters. If we want to monitor something further down, it's not possible. And if our wind turbines give us higher frequencies like 5 Hertz, then we are limited to 100 meters. So it is an advantage and disadvantage depending where our target is.
Yeah, I've got a question regarding here I am.
Sorry, I was looking.
Monitoring resolution, you are saying it's better using that interferometry. I remember from what I know in my lectures on seismic that there is always problem to catch the layers. They are thinner than quarter of lambda because it's just beneath. And it's normally, if you do characterization, it's kind of like lamina scale or very thin interbeds. Can this help with that?
Well, the resolution is still the same, quarter wavelength.
Okay.
But what it helps with, what we can see here, is because we are closer to the reservoir, actually we get higher frequencies still there. And then, to compare it, and then we can see thinner layers. And that's what we see here in the left. compared to the surface data, so the sources from the surface, receivers at the well, and then our imaging quality is this. And here we clearly see that our wavelength is longer, so we can see thicker layers, not the thin ones. Yeah. No. Yeah, well, it depends. What Eric was hinting at yesterday, so if we start looking at amplitudes and then amplitudes versus angle or offset, then we start extracting other things. And then, yeah, we can characterize possibly a thinner layer. There are other ways as well to get a super resolution, but yeah, how practical they are, I'm not sure. Yes.
Hi, Deyan.
Hi.
Good to see you again. Thanks for your presentation. So you've been talking about imaging the structure itself, right? So what about imaging what happens inside it? For instance, if you inject hydrogen and withdraw, is there a possibility to do something there with this technique to image the actual fluid propagation through the medium?
Well, that's the target. And that's one of the questions that I will just bring to the audience, what I started with. Are we ready to monitor and we know what will happen, or we don't know what will happen? Do we need actually monitoring then if we know what will happen?
Let's ask the question differently.
Yeah.
Is this technology suited for that, or can it become
can
suitable?
Be suited.
Or is there other technologies that can do this? Because
so it can be suited. Let's make such a mind experiment. If we have a well close to our structure, so let's take it, well, if it is a salt, for example, if we have a well that goes above the salt, and then we redate them close to the salt, then possibly we should be able to see where the hydrogen is. Again, it depends what Eric was explaining yesterday, what is the difference in percentages between the normal gas that is there, or fluid, and the hydrogen when it is injected. If they mix perfectly, then we might still see from the top of the salt, so top of the reservoir, different amplitude of the refractions. And then you might say that something happened there. And then again, you remove the hydrogen, and then the amplitude changes, and then you detect that something changed. Of course, geophysics itself cannot give us all the answers. That would have been great, but it's not possible, so we need the rest of the public here to start saying why it changed the amplitude of the seismic wave.
it's clear. It's a method, of course, to image something, but I'm encouraged by your answer. Thank you.
Yeah. Thank you. But okay, so to say again, this question, are we ready to go and monitor? Do we know everything?
Actually, I wanted to ask you a question from online as well.
Okay.
That imagine you wanted to now do hydrogen underground storage, and you have unlimited resources to design your best monitoring scheme. What would you do?
Several things. If we want to go for active sources and then receivers, so have receivers at the surface, sources at the surface, really, as I explained, possibly cemented so that they do not change. Still, we might have changes in the subsurface, near surface, which is always a problem. Then also in parallel to have a few wells. If we talk about salt dome, then a well above it, a few wells on the sides, and then record from the active sources, use really advanced seismic methods for imaging and velocity information extraction. In between those surveys, possibly use passive sources to see if there is some change, continuous or not. Recording in the wells with optical fiber. In the surface, possibly yes. If we use three-component optical fiber, if not better to use three-component seismic receivers. No, I think that's not a big wish list, right? Can be done.
You were just speaking for 5 minutes. I guess you listed quite some instruments, which is good. Any other question, or I go online? How accurate it is to monitor the stress, in situ stress, and the state of the stress near the cluster of salt caverns?
I do not have experience with salt, to say, but what we did now, modeling experiment for seismic interferometry to see, together with my colleague Auke Barnhorn and his PhD student Aukje. Yes,
they're both here.
So they measured in laboratory changes in the rocks due to the changes in the velocity of the rocks due to stress change. And then we used seismic interferometry, a different application of seismic interferometry, to try to see that change with sources and receivers at the surface, and we could see it.
What is the biggest challenge to do that in the lab, to get the right quantities? And would it be feasible to do it with hydrogen? Would you consider anything? How can you introduce yourself?
Good afternoon, I'm Auke Barnhorn, here a researcher in Delft together with Deyan and Hadi. The biggest challenge with hydrogen, I think, is I think that comes to the same question or the same point that Deyan alluded to. How much does the hydrogen change the properties or the seismic properties of the medium compared to the water? If that is, or the gas or whatever that is in there, if that's tiny, and then it's very difficult, I think. If there is a significant change, so maybe that's the first thing we should show, that there is a significant change in velocity, and maybe also, but it can also, if it's not in velocity, there may be an amplitude of the seismic wave. If the properties of the seismic wave change due to hydrogen and due to stress in terms of amplitude or in, I don't know, in how the wave propagates through the medium, then you might pick that up. It's not necessarily only velocity, I think.
Another question, Stefan?
Well, thank you. Listening to your wish list, do we do the same procedure when it comes to natural gas storage? Is it worth the effort, or is there any difference in storing hydrogen and methane? Because we do not do the procedure in our operation.
It is the same procedure, and I would possibly speculate that with methane storage, so natural gas storage, it would be easier because this is something that we know already. How much it can change, we have the models to calculate.
Is it the difference between academia and operation, or do you know, how would you do that?
Of course, we have a seismic of our depleted fields or our fields. They are, we have them from let's say production.
Yeah, exactly.
But we do not have a constant seismic observation of our.
So that's the
storage
wish
operation.
List. So to be able to monitor, we have to make the monitor survey, and that is something that maybe we should add to the wish list as well. That first we start, that we have a monitor survey, and then we plan how to make it. If we don't have that data, of course, we cannot say anything. But to answer your question, yes, we can apply the same techniques with active sources, what Eric was mentioning yesterday, with passive sources, with seismic interferometry, and then try to image specific parts or the complete reservoir to monitor it.
Another question from my phone now is that apart from stress and all the other kind of typical things we would like to monitor, also we would like to monitor microbiological, geochemistry, and all others as well. Now, monitoring is wide when it comes to hydrogen storage, so chemistry should be also monitored, microbial activities and other things. Can the two monitoring schemes come together and do monitoring the same? Obviously not waves, we don't do wave analysis for microbes, but is there anything that we could do the two fields come together?
I think so, yes. Actually, as I said, and also what Eric was mentioning yesterday, to interpret the seismic data, we need extra data. We as geophysicists, it would be great. We deliver our seismic image, and we go to have lunch because we finished our job successfully. So it's your problem now. But it's not like this. So we need to interpret those results, and that will happen by monitoring the other changes so that we can start discriminating what happened and what did not happen. At least that's how I see it. Of course, I am not at all into chemistry and biology, so I cannot say it, but I think at least that it will be very helpful to do the things concurrently, in parallel.
Bart?
I guess the answer is no, but would there be a possibility to use this also in detecting spots where you might have leakage, really?
I guess the answer is yes.
Yeah?
Yes. It is possible, depends again how much is
the
leakage.
resolution, I guess, right?
Yes, exactly. So it's a question of resolution. There, it might help if we have this type of monitoring that I mentioned about the surface waves. So it is called coda wave interferometry. It is not seismic interferometry, it's different, but part of the name is the same. And with that, one can really detect velocity changes in the subsurface down to 0.1% even. So this increases the resolution. And then that could be an early warning that something is happening. It will not say exactly where it happens, but it will at least say that something happens. It can be used with surface waves. It can be used with reflected waves. The advantage of using reflected waves is then at least we start saying where it might have been happening. Surface wave will say it happened between the surface and the depth to which the surface wave can see, let's say 300 meters. The reflected waves, if they're used, multiples, what Eric was saying, it's good to use multiply reflected waves, then can tell us that it did happen somewhere in this layer or in this package of layers.
Understood. The reason why I was asking was triggered by the combination of microbiology, because I think if you combine different techniques, including this one, but also from microbial means, we have some ideas to assist in leakage monitoring, let's say.
I agree.
Then you have a good overall technique, I guess,
Yeah.
with some good resolution. Thank you.
Okay, so let's thank Deyan once more. Thank you very much.
Okay, thank you.